and it's time to start. So I will chairing this session, and first speaker will be Abhishek Srivastava.
Okay, thank you very much. So, good afternoon to all my colleagues here. I'm Abhishek Srivastava from Department of Physics, Indian Institute of Technology, BHU, Varanasi. And today I'll be speaking on flares and quasi-periodic pulsation in some stellar coronae. So basically, I would talk about the stellar flare and related QPPs and their physical implications. And then I will try to emphasize on the point that how important this area of research is. And multivalent observations can inform more informations there in that particular arena. So basically, I would start with a very primitive slide or very basic slide. And this basically telling that sun is the only star in all the population in main sequence that is well studied spatially. Like it is the only star which is spatially reserved, and we can understand the greater details of its atmosphere, corona, and various parts of the lower atmosphere. So you can see here that just a minute. Okay. Okay. So you can see here that there are SOT observations of flare in near the sunspots. These are the flare ribbons. So finer details could be observed by high resolution observations. And then AIA, SDO AIA images are also showing the flare energy release in the solar corona. So the emphasis is on the point that we can have the greater details of the flare spatially in the sun, and we can then constrain on the various physical processes, ongoing physical processes in the flaring region. But when we observe sun as a star, so we can get the typical flare response curve, light curve. Likewise, the one which is shown here in this bottom panel, this is the solar flare and related light curve in the microwave emissions, and it is the work from Elena's paper. Okay, this is in 2020, and this clearly depicts about the different phases of the flare. For example, the pre-phase of the flare, then rise phase, and then its peak as well as the decay phase. And the decay phase of the flare is clearly associated with the quasi-periodic pulsation. That means something unique physical process is going on behind the flare energy release. So that is the typical scenario when we observe the sun or its flaring region in form of a star mode. Not only the sun, but when we inspect the main sequence of the HR diagram, so we find lots of flaring stars. So compared to the sun, when we see the right branch of the main sequence, which is basically the low luminous cool sun-like stars, they exhibit flare, and at multi-wavelength, they sometimes show QPPs, quasi-periodic pulsations, which are linked with the physical processes in their stellar coronae. So these stars, as we are well aware, that they are M and K stars, which will have convection from the interior, and that basically causes the fanning out of the magnetic field which is generated inside the star, and this will form its exterior, that means magnetically dominated atmosphere, and particularly the stellar corona. And these stellar corona, they can have the flares and other eruptive processes, likewise the sun. So basically, most of the flares are observed here in this branch of the main sequence, which is basically associated with the cool stars and dim stars. But when we carefully inspect the left side branch of the main sequence with respect to sun, which is dominated by A and B class of the stars, so oppositely, they have radiative envelope in their interior and do not possess magnetic corona in the exterior, because magnetic field is not able to transport over the outer atmosphere. But these stars may have fossil field, and these fossil field would be the remnant of star forming process, and they can lead some localized transients in their atmosphere. But from the Kepler data of white light flare, it was observed, it was shown by Bellona that the incidence of flares on stars drops by a factor of 4 from K to M to A to F stars. So basically, when we inspect or observe the entire HR diagram, so the sun-like flares are mostly dominating in the cool stars, are basically the solar-like stars in that right-hand part of the sequence, while the bright and these stars, hot stars, which are A and B stars, they are having the transients, but they could not be the sun-like transients or something like that. Apart from this main sequence, when we inspect the flares in the pre-main sequence, so we find that some rapid rotators, they may host the flares, the solar-like flares. So some pre-main sequence rapid rotators, like for example, Abhishek, they can host the flares. And since they are rapidly rotating the stars, so they have a stronger field and they can have powerful solar-like flares. So this is the overview over the different classes of the star, which can host the flare or flare-like transient events and so on. Basically, when we go and try to understand why these things are happening in the stellar atmosphere, so the key is the atmospheric magnetic activity, which is generated and transported in form of magnetic field from the interior. So is well-known solar magnetism, basically, when this dipolar magnetic field from the interior, that would be converted in the toroidal. This is poloidal field. This is, with time, this will be converted in the toroidal field, and they send to the photosphere the different active regions, and those active regions could be the host of the solar flares or eruptions. So this kind of dynamo could be in some stars, but of course they can have some different dynamos also. So the key is the magnetic activity, key is the magnetic field which is generated in the interior, and due to the flow and differential rotation, they could pop up in form of active regions in both the hemisphere, and they form the active regions, and they host the explosive events, or you can say the transient events in form of energy release. And one could be the larger event, larger energy release in form of flares. So if these stars could be observed apparently in the greater details, so they can show this kind of behavior which we usually observe at the sun. So their corona can be the host of flare energy release, as well as the eruptions, various eruptions. You can see here the solar prominence eruption, and this is the flare region which is in the vicinity of the prominence eruption. So these kind of eruptions are very likely in the magnetized corona of sun, and of course in the similar stars. Here again, it is the typical scenario of solar flare in the left panel. And then you can see in the coronographic observations that CMEs are there, coronal mass ejections are there, and sometimes flares are accompanied with the coronal mass ejections, but sometimes they may be the isolated events. So magnetic stars which are having the active coronae, they can also be accompanied with the energetic solar-like flares and coronal mass ejections. And this is very interesting stuff to understand about them. So we can understand them in a greater details. Apart from these stuff like eruptive processes, solar flares or coronal mass ejections or prominence eruption kind of things, there are other processes that are inherent in the corona. And for example, the magnetized corona may possess flare energy release, and apart from this, they can have plasma flows, they can form different loop structures, and they can be associated with different kinds of wave motions. So these are the peculiar things about the magnetized corona. These are the intrinsic behavior, or you can say the physical behavior of the magnetized corona, where plasma and magnetic field, they are coupled with each other. So as we are discussing, in the case of sun, we can spatially resolve the different regions, flaring regions or eruptive regions. But for the stars, we only rely on light curve or observed light curves, as well as spectroscopic observations and so on. So here, this is a typical and atypical solar-like flares are shown in the case of Abhishek. So basically the message is that the temporal light curves consists of the wealth of physical information. So here it is the X-ray light curves of Abhishek A for different data sets observing by X-ray Newton, and PN, MOS, and RGS light curves are shown here by blue, black, and red. And here green is the hardness ratio of the flare. So you can see that, you can see from the middle panel and bottom panel that solar-like flares are inherent in the Abhishek also. These are the single flares, and physics may resemble likewise the solar flare and so on. But apart from this single flare, a typical solar-like flare, there are some complex flaring events are also there. You can see that the top panel where there are multiple flares, but these flares are not well resolved, and the decay phase of one flare is intermingled or diffused with the rising phase of another flare. So you can assume the energy release scenario there and hydrodynamic conditions there. I'm not going to discuss the details of this data. This is just to emphasize the stellar flares here. But this is one work which is being done by my one student, Sweta, and this we will communicate soon in the MNRs. So these kind of flares, which are typical solar-like flares or atypical flares, they are occurring in the solar-like stars. Now I would go and show you some very interesting stuff, which is the flare in different stars. Basically, they are the red dwarfs, and these flares are observed by Zeri and team. And this paper is published in 2018. Myself and Dimitri is also the part of this work. So basically, you can read it out in this table that there are several flares which are basically the red dwarfs, and they are observed by galaxies in NUV waveband, and these are the date and times. And flares are basically shown in these panels. You can see there are single flares or maybe multiple flares. They are inherent over the epoch of time. And the black is the original light curve, while the smooth curves are like blue is running average, this green is pre-flare, yellow is flare, and red is the decay phase of the flare. So there is a clear evolution of the flare peaks in all these data. And once we have done the power spectral analysis by wavelet and EMD, so the interesting information came out that the multiple periods are associated with these light curves. So you can see here that some are the common periods in both the tools, like in wavelet and EMD, and some are uncommon periods. But what is the basic emphasis? What is the basic outcome or emphasis of this result is two classes of physical phenomena. So I write it here, and I show the wavelet of some of these light curves. So the first category is the localized powers in the wavelet, which are repeating less than 3 cycles, and they are associated with the quasi-periodic pulsations triggered in the pre-flare or in rising phase. So basically, those are the very localized powers, and they might be associated with external drivers creating a periodic reconnection in the flare current seat or an impulsive energy release giving rise to an avalanche of periodic burst. So they were mostly or essentially related with the reconnection scenario in the pre-phase of the flare or rising phase of the flare within the current seat, and they are generating such kind of QPPs. And second is basically the global distribution of the powers, which are having greater than 3 cycles repetition, and they are associated with the QPPs triggered in the decay phase of the flares. And we interpret them as a sausage oscillations driven by the external reconnection, or intrinsically they are excited in the post-flare loop system which is generated there in those flares. So basically, these kind of multiple periodicities, when they are studied along with the power distribution over the given epoch of the time, so they can give the interesting informations about the inherent physical processes in such QPPs. This is another example which is here, and this is the flare from the Proxima Centauri, and you can see the flare light curve here. And once here's the decay phase, so there is a pulsation which is inherent in the decay phase, and power spectral analysis is showing some periods which are 1200 something and then 600 something. And the interesting part is that in all the binned data, these periods are available, they are detected, and they are globally distributed. This is the XM Newton observations of the flare between 0.3 to 10 keV band of X-ray on March 2009, 13 to 14 March 2009. And this is basically giving rise the multiple periods, which is also tested by the periodogram. And this is the 1 sigma detection level. What diagnostics we have made using the solar analog here? So the first point is that these two periods are likely due to the impulsive generation of the slow MSD oscillations as a consequence of the flare energy release, especially in the decay part of the flare, while the flaring post-flaring loops are evolved. And using the loop length of 7.5 × 9 centimeter, which is very much close to the solar loop length, we have used the model and use the volumetric emission measure and other parameters, which is derived by for these flares. And then we have measured basically the loop length, and using that loop length, we have calculated the phase speed of the fundamental MSD oscillations for a period of 1261 seconds, which is estimated as a subsonic speed at a given loop temperature of 7.2 MK. So basically, this is the signature of slow magnetoacoustic oscillations or fundamental slow magnetoacoustic oscillations. And the second period, which was 687 seconds, is only present during the first 3 kiloseconds, which is likely to be an overtone that results from the initial spontaneous excitation of the slow mode wave, but damped out more quickly than the fundamental period of 1261 seconds. Okay, using the solar analog and theory of Mackey-1 in 2006, and using the loop parameter and observed period ratio, which is less than 2, we could measure the density scale height, which was 23 megameter for these loops. So the density scale height was well below the hydrostatic scale height for a given temperature of these loops. And this is showing very much similar scenario, what we usually estimate or calculate for the solar loops, which are gravitationally stratified loops. Synthetic light curve, blue, when we include these two periods, they closely match with the observed light curves, but of course some other frequencies may also be present there. So the most important information here is that if we observe convincingly the multiple periods in such stellar flares in decay phase or in any flare phase, so we can at least constrain some crucial physics and related parameters based on solar analogy. I would like to show another example, which is one of the well-known examples, and this is done by Urmila Mitra Krev in 2005. This is the A&A paper, and she has analyzed one flare on 80 micro. Okay, this is low mass star, and then she analyzed the power spectra of this flare light curve. You can see here in this panel, left panel, top left panel, there's a power which is concentrated near the flare peak. Then she filtered this power, this flare light curve in different periods, like P greater than 1200 seconds and in between 500 to 1200 seconds, and then some lower period range. So once she combined these three range of the light curve, she could get the original light curve, the flare, and 500 second to 1200 second band was giving a kind of decaying oscillation, what she estimated in her paper. And that is very much similar to the Sumer slow magnetoacoustic oscillations. And she interpreted these oscillations as slow magnetoacoustic oscillations, and she could diagnose or estimate the loop length in 80 micro where this flare was occurring based on these detected wave modes. So as you can see in several examples, the quasi-periodic pulsations are there in the flare, and mostly they are interpreted as a slow magnetoacoustic oscillations. And there is one more very important work which is done by Sho from Korea, and he has analyzed many X-ray flares and then measured various its parameters, and then he plotted this scaling between the damping time as well as period. And then this was fitting a kind of power law, and a kind of linear relation was developing here. You can see the blue and red was the case for the solar flares. And you can see here that both are matching, are correlating very well. And since this period was increasing and damping time was increasing as well in this relation, so the effect of slow mode wave is patterning in the scaling law. So there are slow waves with the larger period and larger damping time. So they were given the scaling law based on the existence of slow mode waves there in those QPPs, which are in the stellar flares. You can see here one theoretical curve like the one which is given by Shaw in terms of observations. And this is based on linear theory of slow waves by including the all dissipation effects like thermal conduction, viscosity, radiation, and heating cooling imbalance. This is done by my student Prasad, and Tong Jiang was the collaborator here. So in this graph, you can find lots of interesting information. First is this dotted green line, and this is tau equals to P line. And then rest of the data you can see here, like this blue square is the theoretical value between damping time and period for range of the loop with different parameters. And this is for constant heating. And then filled red circle is for the theoretical values with heating cooling imbalance. Black is the Sumer observed data, and empty cyan circles are basically the theoretical values without thermal conductivity, and empty magenta is without viscosity. So you can see this is very consistent with the knowledge what we have gained earlier since last 2 decades. Without thermal conductivity, this curve, the top curve is far away from the Sumer data, and this tau equals to P line. That means the viscosity effect is not very much prominent in dissipating the waves until you have very high temperature or very small length of the loop. Fine. But as you see, when you include thermal conduction, so they are coming closer, and heating cooling imbalance is making it more closer to the observed data. But of course, there is not much mapping over the observed data, but they are coming closer. And I have put the fundamental slow oscillatory Proxima Centauri as reported by Srivastava et al. Here. So you can see this is lying near the tau equals to P line, and I overplotted the triangle, green triangle, which is the data from Shaw, and it is lying very near to the observed value and very near to the theoretical curves what we are predicting here by this linear model. So basically, this top part, higher period part and higher damping time part, can be utilized for interpreting the observations of slow microacoustic waves for the stellar loops, which are assumed to be higher loops or longer loops, and we can use this larger period and larger damping time part to predict the magnetoacoustic oscillations for those loops basically. So this is the
3 minutes left.
Okay. So apart from the wave, there are some other scenario also. So Fabio Real in 2018, he simulated the sloshing back and forth plasma motion in the stellar loop, and he matched this with the observed periodic modulation of the emissions by using Chandra ACIS observations from V772 ORI. So what is this basically? It is very similar to the observations and models which are showing that in the solar atmosphere, flare heated sloshing back and forth of the plasma in various loops are there, and subsequent intensity oscillations are reported and probed further ongoing heating and generated dynamics by different workers. For example, Pankaj Kumar, Krishna Prasad, probably Krishna Prasad is going to talk about sloshing back and forth plasma motion. And some of those works, they have interpreted this sloshing back and forth of the plasma in terms of slow macroacoustic oscillations. So still detailed studies required in both observational and theoretical domain. So can this periodic motion resemble with the slow standing wave? Of course, probably we will see in the Krishna's talk about all these informations. But it is very interesting stuff which one can explore in the context of stellar loops also. And this is another very important information that I want to put here, I want to emphasize here, that QPP periods were not correlated with the stellar temperature, radius, and other things like rotation period or surface gravity, especially in the cool stars. In the cool stars, strong magnetic field and related activities are predominant, which may lead powerful transient phenomena in the atmosphere, for example, flares and waves, etc. I would just summarize the stellar QPPs associated with the MSD wave and oscillation related interpretation. Probably Valerie is going to talk about all these things and their seismology aspects in the next talk. So you can quickly see that there are plenty of works related to QPPs in different bands like optical bands and many other bands, radio bands and so on. Basically, they are reporting the multiple periods and single periods from the shorter period duration to the longer period duration, and they are interpreted in terms of various MSD oscillations. You can see all these lists. So it is only where the MSD waves and oscillations are considered as a viable interpretation. So my punchline is that, of course, MSD waves and oscillations could be one of the possible physical mechanism behind the observed QPPs in stellar flares or solar flares, but there are many other processes that could be leading the QPPs, and some are listed here and well described in the recent review article by Ivan in Space Science Reviews. You can see here all the details. They are like waves, like sausage oscillations, kink oscillations, torsional oscillations, or slow mode oscillations, but they could be other mechanisms too. For example, if there is twisted loop with current and it is oscillating, so JetSave LCR circuit equivalence could be used in interpreting some those aspects. Apart from that, periodic reconnection can also lead some kind of QPP variations there in the flare. Auto wave processes could be there. Flapping oscillations can be there above the arcades where small scale reconnections are taking place. Some self-oscillatory processes can also be, resumed there in the flaring region. You can see these cartoons where numbers are put upon regarding these processes. Thermal overstability can be there when heating cooling imbalance is there. So this could lead thermal instability, but due to some nonlinear effects, this could be overcome, and its growth could be overcome, and that could lead the thermal overstability that can also cause the QPP. And apart from that, some loop pulses can lead the QPP and some other mechanisms like magnetic tuning fork. So my message is that QPPs are linked with the various physical processes mechanisms in the solar atmosphere, whose studies are now significantly developed, refined in last 2 decades, especially after the solar trace observations when MSD seismology took place in terms of observational data and combined with the refined theory. So with the advent of these high resolution observations and so on, and refined development of theoretical models, it is also playing a pivotal role in enhancing our knowledge about probing the stellar atmospheres. You can see in many examples, as I discussed. The stringent efforts should be continued in this area of research to further develop more the solar stellar connection and related science using multivalence observations. So multivalence observation is needed. I showed some X-ray examples, but in my table, I showed various other bands like visible and radio where people observed QPP. But the main manifestation is that we should use multivalence observations, for example, radio, UV, X-ray, and visible, and we can constrain various physical processes which are linked with the different parts of the atmosphere, whether it is stellar corona or solar corona. Radio and X-ray could be combined as a co-spatial emission in many, its energy bands and our frequency band as radio is concerned, and we can constrain we can understand the same layer where some energetic processes are happening. So this is the important area of research, and this leads the use of MSD seismology, and this leads the probe on the concerned region where flare is taking place and various physical processes are going on. Thank you very much.
Thanks a lot. Questions? Any comments? Question from Ivan?
Okay. Yes, thank you very much for very impressive talk. I have one question. Abhi, are you familiar with solar observations? I mean, specially resolved observations of multi-periodic slow mode wave in solar flare loops?
Actually, we tried with EIS, the slot observations long back in 2010, and we derived the light curve from from the apex of the loop system, UV loop system, and near the foot point, not exactly at the foot point, but above the foot point, and we did power spectral analysis. We got true periods, which are very much like to the harmonics of the slow oscillations. But our worry was that it was a typical 1 MK to 2 MK loops. And basically these oscillations, they are reported in hot loops by Wang and company. So then there is one theoretical model, which is basically the forward modeling by Bratsa and Yura Taroen in 2008. And they by using their forward modeling, they predicted that these kind of oscillations, they may exist in typical coronal loops also. So we took that argument and then we interpreted our observations as a harmonics of the slow metacaustic oscillations. But I don't think that any other information is available using any spectroscopy or any other observations about the multiple harmonics of slow waves. Because it's very hard to excite another overtone or modes. But I may be not familiar. Somebody can comment. Maybe Valerie.
Thank you, Valerie. You have question and maybe comment.
Thank you.
Yes, actually, it's so first of all, answering Ivan's question. So Abhi mentioned the Sloshan oscillations, and essentially Sloshan oscillations are multimodal, so otherwise they can't exist. So hence the question is not how to detect multiple periodicities, but how to suppress damping of high harmonics in Sloshan oscillations. So this and now my question to Abhi. So slow magnetoacoustic oscillations in the stellar context. So just imagining it's observations without any spatial resolution. So hence, if you have a loop, with the plasma performing acoustic oscillations there, so essentially the same plasma always remains in the field of view, because it's so bigger than the star. So how in this case we can get the modulation of the emission? So if all the plasma is always in the same field of view. So the only idea which I can have is that the loop is near the limb and a half of the loop or something like that is just beyond the limb. So yeah, the appearance and disappearance of the plasma in the field of view. Is it the only option, or you may think about something else?
Yeah, you are right, Valerie. I think this is one of the major constant. Basically, once we try to interpret these stellar observations, so generally when we make the loop model, so we just consider the static loop system, single loop system or something. But of course, this is not considered.
Yeah, no, I think so. This forward modeling is very simple and necessary, actually, because if you see only a part of the loop, so hence the signal would be quite, affected by this, and it could, shed some light on what is going on.
Yeah. Okay.
Yes. Okay. Thank you. Maybe short question. I'm interested mostly in radio bands, and could you estimate time scales of periods in radio? Is it seconds, minutes?
In radio, I think there are already observations, especially for the solar flares, and I think Valerie has something in that direction in 2003. So basically, they are short periods, like few seconds or few tens of seconds. And those QPPs, solar QPPs, are interpreted in terms of sausage oscillations. So there are several papers where these short period oscillations are there in radio, and they are interpreted in terms of sausage waves. And it is also listed in Ashwandan's book. So these literatures are available.
Okay, thank you.